Welcome back. We've been talking about the limit of a function, and then we recently put in this concept of what it means for a function to be continuous at a point C, and we used the definition of a limit in order to define what we mean by continuity at a point C. And what we're really kind of talking about is the smoothness, intuitively the smoothness of a function of x. And again, as I told you, a lot of theorems, and we're going to look at our first one soon, we'll start off assuming the function is continuous. In reality, you know, what are we using these functions for? We're using functions to model real life, right? We talked about we're modeling real life, and in real life, it's very difficult to, nature usually produces continuous functions. You might see a function like this, you know, in a mathematical textbook. I can't imagine how that would model what's going on in nature. Maybe some vertical asymptotes might occur, might be good models, but for the most part, most functions are continuous. You'll see polynomials are continuous, trigonometric functions are continuous, root functions are continuous. Now, there's one thing I want you to remember in this continuum of smoothness. I want you to put this little graph in your mind, and I'll try to do it with a magic pen. Oh, I thought I had some. Well, okay. Thought I had some colorful pens here, crazy pens. But I want this to be a continuum. This is my little line, continuum of smoothness. As I go from, okay, I'm back, and I found my creative pen here, and that's what I'm going to use, creative pens. And this is my smoothness. Okay, see how smooth this is. Smooth increases as I go right to left. Now here, in this part here, you'll see this would be the limit exists. Remember, the limit exists here, and then the limit has to exist for it to be continuous. Now here, if it's even more smooth than that, at this point here, we say it's continuous. All right, so notice the graph goes from right to left. What I mean by that, if a limit exists, it doesn't mean it's continuous. But if it's continuous, if it's smooth enough to be continuous, then the limit must exist. We'll put up another thing up here soon, and this will say, is it differentiable? But we'll do that soon. So again, when you talk about smoothness of a function, the limit has to exist for it to be continuous. But if it is continuous, then the limit has to exist. Again, you'll see a lot of multiple choice type questions where they want to test that concept. If it's continuous at C, the limit has to exist at C. Okay, our first theorem in calculus, we've reached it. It's called the intermediate value theorem. Simple if I show you a picture. Again, we'll put some words down. Here's the text of it. And we need to decipher this a bit. Nothing difficult. It says if f of x is continuous on the closed interval, notice this is closed interval AB, and so we know what continuous means. We got a mathematical definition. We also know you don't pick your pen up. And we have a value n, a y value n, that is somewhere between f of a and f of b. It could be, could be it this way, f of b is greater than f of a, or if f of a is greater than f of b, n's in between. Then there exists an x equal to c. There's a point x equal to c between the x points a and b such that f of c equals n. Okay, what does that mean? Let's just let's draw a picture of that, make it a little simpler. We're saying here, Go back to a reasonable pen, away from the crazy pens. We got a point A, and we got a point B. And f of x is continuous, so I put my pen down in A, and I draw to B. All right? Now, if, in this case, what it says is if I pick some value of n between these two, I had to get from A, and I could have got to A. Let me change colors here. I drew that maybe a little bit. I could have got to A that way, but if I don't pick up my pen, you know, I can squiggle around and squiggle around, go up and down, all like that, okay? But I go from A to B, that means if I pick any value here, if I pick some value here, n, okay? Since I went from, this point here is what, f of A? This point here is f of B, okay? Since I'm going from f of A to f of B without picking up my pen, so I'm go from here to here to here, I have to go through n because I didn't pick up my pen. So that means there has to be at least one C here where this occurs. And here you see one C, 2 C's, 3 C's, 4 C's, 5 C's. Here on the blue one, you only see what? Well, here I only see one. There's one there. Versus here I got 1, 1, 2, 4, 5. Okay, that's what the intermediate value theorem says. That's all there is to it. All these points must exist. It's kind of an existence proof. Okay, let me show you an example problem where the kind of problem you'd have to work with using. Okay, we just talked about the intermediate value theorem, and this would be a type of problem you might see for homework. Would be they're giving you a function here, give you a function, and this is a polynomial function. Okay, we know polynomial functions are continuous. This is a continuous function. It says show this function has a root. A root meaning, well, I actually put the root right here, I guess, when I wrote it out. The function's equal to this. It having a root means it's equal to 0 between x equal to 0 and x equal to 2. Well, how do I do this? I say, well, what is f of 0? Say f of 0, I put in 0, 0, 0. It looks like that's minus 2. And I'm picking easy numbers. I don't pick fractions because I don't want to work that hard. I'm going to put in a 1. F of 1, I'm going to get 4 minus 6 plus 3 minus 2. That's going to be minus 2 plus 1 minus 1. Okay, minus 2 to minus 1. Well, how about f of 2 then? F of 2 is equal to 4 times 8 minus 6 times 4 plus 6 minus 2. Okay, well, what's that going to be? That's 48 minus, that's 24, so 24, I'm seeing 30, I'm seeing 28. I see that that is equal. That's equal to 28 if I've done that right. So this is positive. Notice that's positive, this is negative. If I looked at this function f of x, what would I see? Well, at 0, let's change colors here. Let's go back to green. At 0, what is it equal to? Minus 2. Okay. At 1, it's equal to minus 1. At 2, 2, it's up here. It's like 24. Okay. So here, if I draw, notice it's continuous. So I start here. It's continuous. It can scriggle like that. It doesn't, by the way. But it could. It's continuous. And here it could squiggle somewhere in here. But at some point, it has to cross, okay? It has to hit 0. So there has to be, an x. Actually, in this case, there has to be an x between 1 and 2 such that f at x is equal to 0. Now notice a lot of times you'll see this, okay, there's a c value in here. I'll put a c value in here, and that's the c value that we found. Okay, so here's an existence proof. We know there's a 0 here. Existence proofs are somewhat useful because then if you know it's there, you know you can look harder for it. Okay. Okay, just a counterexample again, because we're talking about continuity. Notice, if somehow the function wasn't continuous, say the function isn't continuous, then it could go here. I could pick up my pen and go like this, okay? So in this case, this red is not continuous. And if the function isn't continuous, I cannot guarantee the function in red is ever equal to 0, okay? But if it is continuous, as it is in green, since I'm not lifting my pen, I have to cross through the 0 point. Okay, thank you. See you soon.